Okay, hello. So this is the last video. We're going to do some problems from Module 10, and I'm going to work through some of the extra problems on page 574. So hopefully these will help you if you get stuck on the on your owns or the practice problems in the chapter. So the first one just says that an 8 centimeter long spring has a spring constant 250 newtons per meter. How much force is required to stretch the spring to a length of 11 centimeters? So, as always, I recommend drawing yourself a picture so that you can understand what's going on. I have an 8 centimeter spring, and I'm going to go ahead and convert that right to meters because I know I'm going to need that. And I know it has a spring constant of 250 newtons per meter. And it says how much force is required to stretch the spring to a length of 11 centimeters. So it's going to go to 11 centimeters or 0.11 meters. And so I want to know what is the force. So I know that the formula that I'm going to use is force equals the spring constant times the change in x. And so then I have to think, what do I have? I'm given the equilibrium distance, which the resting spring is 0.08 meters, and I'm going to stretch it to 0.11 meters. And so my change in x is going to be the x final minus the x initial. So it's going to be 0.11 meters minus 0.08 meters, giving me a delta x of 0.03 meters. And then I can just simply plug and chug this into my formula for force. So it will be that, I can say that the force equals the distance times the negative spring constant. And so that would give me an answer of negative 6.15 newtons. My meters will cancel. And so it tells me that the force is going to be applied downwards at a rate of 2.15 newtons in order to stretch that spring 11 centimeters. Okay, the next problem I'm going to look at is going to be, let's look at number 4. So number 4 says, what is the mass of an object? I'm going to look for mass of an object on a spring that vibrates back and forth with a period of 0.95 seconds. And its spring constant is 18.2. And so I want to find the mass. So what do I want? What formula do I want to look for? I know I need to find mass. I have a period and I have a K. And so I'm going to, and I was told that it was on a spring. So I'm going to use the formula. It says the period is equal to 2 pi, the square root of the mass over the spring constant. And I am going to have to rearrange this to solve for mass. So we did that in one of the other videos. Hopefully it makes sense to you. I'm just going to go through quickly. We square both sides to equal 2 squared pi squared m over k. I'm going to get rid of my k over here. And I'm going to move my 4 pi squared over there to rearrange it to solve for my mass. So now I can plug my information that I'm given into my formula. 0.95 seconds squared times my spring constant. Please do not forget to square your values, which squares your units as well. And then this gives us 39.5-ish, no units. And then plugging that all in would equal 0.42 kilograms. So again, our units, we have our kilogram meters per second squared our meters cancel, and then our seconds squared cancel, leaving us with kilograms for the units. So the hardest part of this one was simply rearranging the equation. So I hope you get comfortable rearranging that equation with the radical in it. So let's look at probably the most tedious of these is going to be the energy ones. And so I'll go a little more slowly on this one. We're going to do number 8, which says that a spring with a spring constant of 1.51 newtons over meters has a 2.46 kilogram object hanging on it, and the object is pulled 11.8 centimeters. I'm going to go ahead and just convert that already. It's pulled 11.8 centimeters from its equilibrium point. So since it says it's already been pulled from its equilibrium point, I know that that is delta x, or it can also be the amplitude. Remember in the last one we talked about how the amplitude and the delta x can be the same thing if that is the highest distance that it's pulled away from the equilibrium point. And so then it says it's pulled away from that equilibrium point, and it wants to know what is our object's speed when it's at a new distance of 0.1 meter from the equilibrium point. So if we want to draw ourselves a picture of this, we have a spring that has an equilibrium point. We're not given the equilibrium point on this one. We're just told that it's pulled away from its equilibrium point, 0.118 meters. And we want to know its velocity at 0.1 meters. So we can see that it's pulled farther away, so this can be our amplitude. We could find also its velocity at this point, but that's not what the question's asking. The question's asking what is velocity at this point. So we have a couple things that we can do. We can find the total energy for the system, which would be all potential at this point. But we have a nice formula for that. If we have the amplitude, the total energy is 1/2 the spring constant times the amplitude squared. So we have that information in order to find this. And so we can find that the total energy of the system, and remember, it's all potential at this point because there's no motion. Okay, so if we can find the total energy, that would be the total energy at any point in the spring's motion. So the total energy is going to be 0.5 times 1.51 Newton per meter times 0.118 meters, and that whole thing is squared. Again, don't forget to hit the square button on your calculator. And so that would give us that total energy somewhere. If I had written down what I got for my answers here, I would find that the total energy of that system is 0.0105. You can just say 0.01. And our units are energy, so that is joules for that. So our total energy of the system at this point is 0.01. At this point it's 0.01, this point is 0.01. Everywhere the total energy is 0.01. And everywhere we can also say that the total energy equals the kinetic plus the potential. It just happens at this point kinetic is 0, so it's the same thing as the potential energy. But what we want to know is, of course, at this spot here. So what else can we find out about the motion of our spring at that point? Well, we can find the potential energy at that point. We can't find the kinetic yet because we don't know the velocity and we don't know the value for kinetic energy. So we can find the potential energy at that spot at 0.1 meters. And so that will be 1/2 our spring constant times our change in displacement squared. And so it's the same. We plug in 0.5 times 1.15 spring constant times our displacement of 0.1 meters squared. And so that gives us potential energy at that spot of, it's 0.0075 or 7.5 times 10 to the negative 3 joules. So that is our potential energy at that point. So we can then say at this point that our total energy, like any spot, is equal to our potential plus our kinetic. But now we have a couple of those values in order to solve for kinetic energy. So to solve for kinetic energy, we can say the total minus the potential will equal the kinetic energy. And so we can go up here and plug in our 0.01 joules minus our 7.5 times 10 to the negative 3rd joules will equal our kinetic energy. And since I'm almost running out of board, I'm just going to keep writing it here. And so our kinetic energy is going to be 2.95 times 10 to the negative 3rd joules by simply subtracting. So once I have my value for my kinetic energy, I can use my kinetic energy formula to find the velocity. So hopefully I haven't lost you here. Keep in mind what we're looking for is velocity, and we had to find these other values in order to get to our kinetic energy to rearrange that to solve for velocity. I'm going to kind of squeeze over here and do it. So if our kinetic energy equals 1/2 mass times velocity squared, I'm going to put this as 0.5 because I know some of you like it as 0.5 instead. I'm going to rearrange this to solve for our velocity, just like we did before in the other chapters. So I would have my kinetic energy divided by 1/2 times the mass would equal velocity squared. And since I want to find the actual velocity, I would also have to take the square root of both sides to find the velocity. So remember how you have to put that in your calculator, whether you put the radical in first or whether you can find the value and then press your radical sign. So my kinetic energy was this 2.95 times 10 to the negative 3 joules divided by 1/2 of the mass. So way back there, the mass was 2.46, and so it's divided by that value, and then we're going to take the square root of it, and that will give us a velocity of 0.049 meters per second. So hopefully that did not exhaust you and it made sense to you, and you can rewind it and watch it again if I lost you somewhere. But that's probably the trickiest one of these kind of problems. You just have to think about your energy and how the motion relates to kinetic and potential. So you're going to have the most potential before we start our motion when it's pulled as far as it can be pulled or compressed as far as it can be compressed. And we're going to have the highest velocity, the highest kinetic energy when that reaches its equilibrium point. It's let go again and moves. Okay, and we're going to do one more problem that has to do with pendulums. And so we'll look at number 10 as we send the astronaut into space, and you know how we love that. So we have the first astronaut to land on Mars sets up a 1 meter pendulum. So we have our astronaut in his space helmet, and he's got a pendulum here, and he set that up to swing, and it has a length of 1 meter. So when we're talking about our pendulum formula, we want to know the length, and that was given, a 1 meter pendulum with a period of 3.28 seconds. It says, what is the acceleration of gravity due to on Mars? So this is one more, we will solve for the acceleration of gravity because he is no longer on Earth. And if you don't remember the acceleration of gravity due to on Mars, you can set up a pendulum and figure that out so that you can do your physics problems while you're in space. So we do have to rearrange our equation to solve for gravity. So we would have the period squared equals 2 squared times pi squared times our length times our gravity. I just squared both sides to get rid of that. And then we're going to do our acceleration of gravity on that side and move the period over to this side. So if you don't remember how to rearrange that, watch the video before this that talks about rearranging that equation. So let's look at what we're given. We have a length and we have a period, and we know these other numbers, so now it is simply plugging and chugging. So again, these formulas, the trick is just rearranging them. Once you can do that, you're going to find that they're pretty easy. I'd like to have it be the acceleration due to gravity just so that you don't forget what we're talking about, acceleration, not the force of gravity. So let's plug in these numbers. Oh, I forgot our length here. Of course, our length stays over there. So we have 4 times pi squared, which we were doing problems yesterday, is about 39.5, times our 1 meter, and times our 3.28 seconds squared, and we see that that will give us meters over seconds squared, which would be an acceleration due to gravity. And we would find, after doing the math here, that that would equal 3.67 meters per second squared. So that's a fast look at all the problems, and I hope that that helps you to work through the practice problems and the on your owns for Module 10. See you in class.